Welcome, my name is Jason Zane, and this is my Lab 5 project, and my chosen topic is water jet propulsion. Here's a quick look at what we will be going over. And let's get started with the purpose. The purpose of this lab is to understand how water jet propulsion works through observation and application of fundamental physics principles. Now let's take a quick look at the fundamental physics principles we will be using. As always, we will have Newton's second law. But wait, there's more. And that is Newton's third law, which states that for every action, there's an equal but opposite reaction. And here's a preview of our main result. By making some generous assumptions and analyzing tracker data and performing necessary computations, we were able to calculate the force generated by the water jetpack and gain a better understanding of how it works. So now let's get started with the fun part. This is going to be the video I will be analyzing, which I pulled from YouTube Shorts. Before we get started, we will have to make some assumptions and set our initial conditions. And the first assumption we will be making is that the average height for a male is around 175 centimeters and weighs 70 kilograms. So we will be assuming these measurements for our subject in the video. Additionally, a water jetpack usually weighs about 14 kilograms, and the origin will be where the person first touches the water. At this point, the person is starting from rest. The system consists of the person and jetpack only. We will also be assuming constant acceleration and that the system is isolated, which just means that there are no external forces acting upon our system. This is the tracker data, so let's take a closer look at the Y position graph. This is the tracker data, and this allows us to calculate the acceleration, which is equal to the change in velocity over the change in time. We know the initial velocity is 0, so we only have to estimate the final velocity by adding the slope and then calculate the acceleration by finding the change in velocity over the change in time. I chose the time interval between 0.6 seconds and 1.4 seconds because these points lie neatly on the intersection of grid lines, which allows me to easily calculate the slope. Therefore, the acceleration we are getting is actually the average acceleration between t equals 0 seconds and 1 second. Now we finally get to use F equals ma. The only forces acting on our system include the propulsive force from the water jetpack and the force due to gravity. Rearranging the equation, we see that the force from the water jetpack is equal to the mass times the sum of the acceleration due to gravity and the average acceleration of our system, all of which are known. This allows us to solve for the force of the water jetpack, which turned out to be about 1,260 newtons. What does this mean? The water jetpack is shooting out water at an incredible rate, which just means that it's pushing out mass. Recall Newton's third law. Each action has an equal but opposite reaction. If the jetpack is pushing out water, then the water is pushing back on the jetpack with an equal but opposite force, upwards. It's this equal but opposite force which provides the propulsive force which lifts the person into the air. In other words, water jetpacks don't work by pushing off the water already in the lake, it works by pushing out the water. This is true for rocket ships too, except the rocket is pushing out the exhaust they create. This is why rocket ships are able to generate a propulsive force even in a vacuum where there isn't anything to push off of. What if we never turned off the water jetpack? Would we be able to fly as high as we like? As you may have guessed, the answer is unfortunately no. The higher we fly, the more tubing we will need that's constantly pumping out water. This tubing, plus the water that's constantly running through it, adds a significant amount of weight to our system. This means that the higher the person flies, the more weight is pulling him down. Eventually, our system will be weighed down too much to fly any higher. So how high could the person fly? We calculated that the water jetpack was able to generate at least 1,260 newtons of force. Using this, we can calculate when the system would reach static equilibrium. By using Newton's second law and performing calculations, we see that the force generated by the water jetpack could lift up to 130 kilograms of mass. Using our previous assumptions in the person's weight and the weight of the water jetpack, this means that the static equilibrium will be reached when there's 46 kilograms worth of tubing and water being pulled into the air. Now we will make another very generous assumption to make calculations easier. Let's assume that the tubing has a density equal to that of water. Additionally, let's assume that the diameter of the tubing is up to industry standard of 4 inches, or about 0.1 meters. In other words, we will assume that the tubing has a radius of 0.05 meters. Now, the guy in the video flew to about 10 meters, which is more than our estimate of 6 meters, which obviously means that the assumptions we've made have led to some errors, so let's get to that. Some of the errors include but are not limited to the discrete data we collected from the tracker could have been inaccurate due to human error, and also the camera was not stabilized in the video. The system is not actually isolated, which means that our system is subjected to the force of air resistance and wind. We also made generous estimates with the weight of the person and equipment, and the mass of our system was not constant, because it increased the higher the person flew, which we discussed earlier. As a result, our acceleration was not actually constant, which would have greatly affected our calculations. Thank you.